Howdy! Welcome to Aspire Mountain Academy. I'm Professor Curtis, your instructor for this course in Introductory Statistics. In less than 10 minutes, this video provides an introduction to multiple regression equations, as well as multiple coefficients of determination. Let's get started. So a multiple regression equation simply expresses a linear relationship between a response variable and two or more predictor variables. So previously, where we were looking at a simple linear equation, linear regression, now we've got more than one x variable in our equation. So now we can expand our model across multiple dimensions. The general form you see here, y hat equals b naught plus b1 x1 plus b2 x2, and we have a coefficient and a corresponding variable for as many variables as we have in our equation. So it just goes out for as many variables as we have in our equation. There's some notation we need to be aware of. N, as always, is the sample size. K is the number of predictor variables. So if we've got three different x's variables in our equation, then that means k is equal to 3. Y hat is the predictor value of y. So again, y hat is what's coming out of the model. It's what the model produces or predicts. Let's look at this example where we're predicting the height of daughters. So we've got this data here from a random sample of daughters and their fathers and mothers. And we're wondering if we can actually make a model that takes into account the height of the father and the mother and can then predict the height of the daughter. Well, the way we're going to do this is with the multiple regression equation. Okay, and so we're going to input the height of the parents and we're going to output the height of the daughter. Here in StatCrunch, you can see we have, this is the options window when you select multiple linear regression. So here we've got the y variable is what you want to predict. This is what you want to come out with the model. You select your x variables and you can select as few or as many as you like. This interactions section is completely optional. Interactions are simply used to account for the influence of independent variables against each other. The height of the father and the mother don't influence each other at all. So it's not like the height of the mother will change because of the height of the father and vice versa. So there's no interaction that we need to account for here, so nothing's selected. But there are occasions where you may get some variables that are interacting with one another, in which case you might want to check for interactions. And these simply show up as additional variables in your equation. We don't need that, so we'll skip that. We come down here and we hit compute, and that gives us our results. And the results window has everything we need for any of the problems that we might be asked to solve. So here we have a results window from our multiple linear regression analysis. And the regression equation you can see right here at the top of the window. Now notice how they actually use the names of the columns for the data that you selected as the variables in your equation. We can actually shorten that up. Instead of saying daughter, we could say D. Instead of saying father, we could say F. Instead of mother, we could say M. So then our equation looks a little bit more mathematical. We can show it here. The height of the daughter is D. The height of the father is F. And the height of the mother is M. This number out in front, the 7.454, is what's known as an intercept. This is a number, a coefficient, that doesn't have a variable associated with it. And so we call it the intercept. The height of the father has a coefficient. It's the number that appears just before that variable. And likewise, the mother also has a coefficient. So these are the different parts of our regression equation. Notice those same values are listed here in the parameter estimates table in your multiple linear regression results window. If you're looking for a p-value, you want to take it from the ANOVA table. Okay, I know it can be tempting to take it as we've done before when we were looking at simple linear regression. You could take that test statistic and p-value from the parameter estimates table. But that was when you only had one x variable. Now we've got more than one. So sometimes that last variable that you have listed is going to match in p-value, and sometimes it's not. So what you want to do is get in the habit, when you're dealing with multiple regression, of taking your test statistic and p-value directly from the ANOVA table. So this p-value here we don't want. It's the one in the ANOVA table. That's the one we want to take. Note down here we've got, what is this, 2 r-squared values? What's going on with this? Well, what we have here is what's called multiple coefficients of determination. So a perfect fit with our model would result in r-squared having a value of 1. This is the way r-squared is calculated. And you can see here slight difference between the denominator and the numerator in our fraction, but that little small difference makes a really huge difference when you're actually calculating everything out. Of course, you know, if you're ever having to calculate this, you're never going to do it by hand. You're always going to use some piece of software like StatCrunch to do it for you. There's what's called an adjusted r-squared value. Okay, so r-squared is what we've been dealing with up till now. Adjusted r-squared value is a little bit different. The deal with the adjusted r-squared is that the adjustments help us to account for the different numbers of variables and sample sizes between models. So this way we're actually comparing apples with apples and not necessarily apples with oranges. Here's the formula for calculating our adjusted r-squared. So you can see that there's quite a bit of difference here between the formulas, and in fact we have to calculate r-squared first before we can even begin to calculate r-squared adjusted. So this is how we account for comparing models with different numbers of variables and different sample sizes. And that brings us to the end of this mini lecture. I hope you found it helpful. You can find more mini lectures for this and other courses at AspireMountainAcademy.com. Thanks for watching. I'll see you in the next video.